Okay, welcome everybody. Good to see so many people already online. So we've got just a few introductory slides, which Paul Waite is going to take us through. So Paul, over to you.
Yeah, thanks, Tony. Yes, hello, and thanks for joining us, everyone, and welcome to Raycastle's live webinar looking at 5G new radio. In this webinar, we'll be discussing the main features of 5G new radio, together with the advantages and opportunities that this brings to network operators and the industry in general. Next slide, please, Tony. First, a brief introduction to Raycastle for those of you not familiar with us. We were founded in 1958. We initially specialised in radio and maritime communications. We began training the telecoms industry during the 1990s and have established ourselves as a leading training organisation in this field. We have an extensive portfolio of courses covering all the major technologies. We use a variety of innovative delivery formats, from classroom to live virtual classroom and on-demand distance learning. During the past 60 years, we've trained over 300,000 industry professionals from all parts of the industry and across the world, and we're the preferred partner of major telecoms industry giants, a few of which you'll see below. Thanks, Tony. The company's been acquired by new management, so there's lots of new names and lots of new faces around. We've been busy in the last 12 months. We've launched our new Enterprise Online Academy, providing access to all of Raycastle's learning pathways to all our employees within organisations. We've expanded internationally, including a first sale of an academy at a mobile operator in Asia. We've launched a new consultancy division, and pioneered by Tony here, we've introduced the mini MBA in telecoms, which extends our training reach to cover the business of telecoms, including management, leadership, and business model development. All our courses are now available to purchase online, giving you immediate access. You can find out more about us and explore our training portfolio at our website, raycastle.com. Now, today's webinar is going to be presented by Tony Wakefield. Sorry, here you'll see a few of our senior staff within Raycastle. If you'd like to contact any of us, please do so at the email address below. Okay, sorry, Tony, next slide. So as I say, the webinar will be delivered by Tony. Tony's an highly experienced trainer, both technical and telecoms business, as well as a competency development specialist, having worked with a diverse and extensive base of companies worldwide. He has spoken at global conferences and extensive experience in facilitating programs in 5G and wider aspects of telecoms and connected innovation. Before we got into the presentation, just a couple of points of housekeeping. The presentation will last around 45 to 50 minutes, after which there'll be a Q&A. If you have any questions, please post in the chat box, and Tony will endeavour to answer as many of those as possible, although he might need to be slightly selective depending on the volume. Can you all please ensure that you have your microphones muted, just to avoid any background noise? So I'd like to now hand over to Tony for the main presentation. Tony.
Okay, thank you, Paul. Great. So we had to keep that quite succinct because we've got 45 minutes to 50 minutes. Questions, there is a question and answer pod, so use that for the questions, and I've got an eye on that as well. For those who need it, if you want to take my email address, which is just at the bottom of that graphic on your screen now, twakefield@raycastle.com. And if we don't get a chance to answer your questions, please do drop me an email after the event, and we can certainly try and answer after the event. We are recording the webinar, so it will be made available to those who want a recorded version. Okay, great. Right, let's crack on. So 5G new radio, what is it? And you can sort of look around the world, and you can look in different geographies, different countries, and you can sort of assess 5G. And some countries are way ahead. They're really running with pretty advanced deployment now, and other countries haven't even really started looking at 5G beyond just initial assessment. So there's sort of a big mismatch around the world as to what 5G actually means. For me, very often I arrive in a new country, perhaps in a new city, jump in the back of a taxi, and the taxi driver often says, "Why are you here?" And I'll say, "I'm going to teach some 5G." And they always ask the question, "What's that?" I think, blimey, how long is this taxi journey going to be? So not necessarily for the taxi driver, but just generally, what I've done is I've sort of put together a statement which I think sort of encapsulates 5G. Now, you'll probably look at this statement that I'm going to give you in a second, and you'll say, okay, well, you're missing bits here and there, but 5G is a huge topic area. It's dominated by the new radio, by the air interface. So what I've tried to do is just capture the essence of it just through a single statement. So we can start really by the fact that LTE, way back when, sort of 15, probably almost 20 years ago when we first started developing it, telecoms, it wasn't in its infancy. Even cellular wasn't necessarily in its infancy, but we haven't yet got to the point where lots of people were using lots of data lots of the time. We were still sort of constrained by things like price plans and things like that. So LTE was optimized really for relatively big cells compared with what we've got now. So quite big coverage areas, in a very general sense. So what it meant was lower frequencies. It actually meant using the technology that still underpins cellular communications, even now with 5G. It meant specific configurations on something that we know as orthogonal frequency division multiple access, OFDMA. Now, if you're not technical, you don't need to understand that too much at this stage. It's just the fundamental way in which we sort of organize information on the radio interface. But lower frequencies is very significant. If we confine ourselves to lower frequencies, it means that in general, we can use quite large cells. And really, we needed to cover those large sort of coverage areas. Hence, with the limited processing that we had 15 years ago, it made sense to, in a very complex system, keep it relatively simple. And it's only relative to what we've been doing fairly recently, but keep it relatively simple and just go for a really simple sort of configuration for this OFDMA. Okay, so now if we fast forward 10 to 15 years, when we start looking at 5G, things have moved on. Processing is, we can process faster, lots of developments in terms of the silicon level. But crucially, the dynamic has changed. So operators have spent the last 10 to 15 years looking at LTE and densifying the network, so putting in more base stations. Now that's really interesting because not only are we sort of now catering for worst case, we've also gone to a point where in major cities, perhaps, lots of customers are on average quite close to the base station, which means that some of these assumptions that we needed for LTE, where we needed the big cellular coverage areas, in certain places, they're not there anymore. We are talking about smaller cells because we need more cells, because we've got more customers, or we've got more customers using more data more of the time. So customers are now, on average, much closer to the base station. So what that means is that we're no longer constrained by the frequencies. So we don't have to use those lower frequencies. We can start looking to use higher frequencies, different places of the within the spectrum where there's lots of additional capacity. We can start looking at higher frequencies where there is lots of spare capacity. As we move up the frequency band for cellular communications, the size of the antennas reduces. So the size of an efficient antenna becomes smaller, and it's sort of proportional to the frequency, if you like. Sorry, inversely proportional to the frequency. So we can start using some of these advanced and very efficient antenna arrays. And that's where some of the real magic of 5G comes into play. If we can start using those really advanced antenna arrays, so lots of small antennas together at the same time, rather than one single antenna, or perhaps just a few antennas, suddenly we can start looking at the mathematics of it. We can start playing with constructive and destructive interference. So we can start forming beams, or we can start focusing the energy. So far what we've said is, throwing off the constraints of LTE, suddenly 10 to 15 years later, we can start looking at a much more flexible way of providing coverage in the network, which means we can use different parts of the spectrum where there's lots of additional capacity. And if we do use those different parts of the spectrum, we get some massive advantages in terms of antenna use, focusing the energy. But to do all of that, we need to change the configurations. We can still use OFDMA, this thing as a technology, as a foundational technology, is absolutely fantastic. It's very, very efficient. We can still use it for 5G. We are still using it for 5G, but we don't have to be quite as constrained, i.e. we can use different configurations. Now, when we use different configurations, we need to do that because that's the way in which we can efficiently use it at the higher frequencies. So I think what I've just painted, and obviously I did say initially that that isn't suitable for the taxi driver, but for you guys in the industry, probably a lot of you, I know there's a lot of people on the webinar with a lot of knowledge of cellular and of 5G as well. I think that hopefully makes sense. So we can leave behind the worst case scenario. We still need to cater for that, but suddenly we are talking about very diverse deployment scenarios where customers can be very close to the base station. We can start thinking, therefore, about much higher frequencies because we're not constrained by using the long range, lower frequencies. It means we gain access to all these advanced antennas, which give us a lot of the efficiency that we need from 5G compared to 4G. But we have to change the radio interface. Now, that's an opportunity. We have to change the interface if we want to gain access to all that efficiency. So while sorting that out, the opportunity is to go a little bit further and sort it out a little bit further to give us latency, reduce latency, increase reliability, better energy use, perhaps allowing us to offload onto small cells more easily. Lots of things that we can do within the system just to give us some additional advantages. So that's the statement, that's the rationale. It's very wordy. It's not particularly great to start a webinar off with a rationale like that. But to be honest, we need somewhere to start. So we can put some more meat on the bone, as we say. In the UK, we can perhaps start looking at the bandwidth, the frequencies. So whereas 4G, the spectrum was sort of constrained to a fairly well-defined part of the spectrum, anywhere from sort of 700 megahertz, perhaps up to 2.6 gigahertz, so somewhere down here. With 5G, it's much wider. It's not as well defined. It has to be specifically defined for the actual bands themselves, but in terms of where we end up with in terms of 5G, there's lots of research going on to look well beyond where we're currently using 5G. But so far, we've identified frequencies right the way from sort of 410 up to 7.125 gigahertz, and then starting again up in what we call the millimeter wave. So the millimeter wave at 24.25 right the way up to sort of 70 plus gigahertz. That is a step change compared to 4G. Why have we done it? Well, because there's lots of spare capacity up here, lots of capacity that can be made available to cellular communications. Why have we not done it before? Well, it's what we said earlier. This is much higher frequency. The range, the usable range at higher frequencies is a lot lower. So when we developed 4G LTE, we went for worst case. We needed fairly big cells. But here we are 10 or 15 years later, 4G already gives us a really good sort of coverage layer. We can start thinking about capacity, extra capacity. The really good thing with 5G is it's a single flexible design, and it covers that wide spectrum or the wide range of spectrum scenarios. Initially with 5G, we've specified 2 frequency ranges. Just because they sort of fit in with what we're trying to achieve with 5G. So good, long range coverage for quite big cells, all the way up to very specific sort of much smaller cells, or even sort of beams, which give us perhaps inside a factory, it gives us good coverage, but with very low latency connectivity. And we support high data rates. So increased capacity, much greater efficiency, whereas LTE, we sort of split the actual bands up into no more than about 20 megahertz. I say about because we've got things like carrier aggregation, which can extend that, but 20 megahertz for a single band, for a single carrier. That's probably the better terminology. So 20 megahertz for a single carrier. Well, in 5G, we can go up to 100 megahertz or even 400 megahertz, potentially. It depends on the actual geography, it depends on the regulator, it depends on how much spectrum is being made available by the government / regulator. But in terms of the standards, these are the sort of upper limits. And of course, we know it gives us access to the advanced antenna techniques, which then allow us to beamform or use this massive MIMO, multiple in, multiple out antenna systems. Now, these two together, highly complex, but in terms of concept, it's quite simple, really. All we're trying to do is focus the energy. You can imagine a base station from years ago, perhaps an omnidirectional base station, still plenty of them around, but initially this was how we provided coverage in a cellular network, just omnidirectional, so perhaps a tower structure giving coverage in all sort of 360 degree directions. It's great, good coverage, but it's not focused in any way. But what we can do here with 5G is we're in a much better position to provide that sort of general, really good coverage, but also at the same time, perhaps via some of the higher frequencies or mid frequencies, really focus that energy to provide the capacity where it's needed. So we get we have the possibility of really flexible 5G deployments. Firstly, with 4G. 4G is using the same fundamental technology, or FDMA. It's been deployed over the years to give us really good, solid coverage. So why not use it with 5G? So 5G can be used as an addition to that 4G network, so non-standalone 5G. And then in time, and in some networks we're already starting to see it, so just a handful of networks worldwide, we can start using 5G by itself. I mean, whether you'd actually do that initially, you certainly wouldn't rip out a 4G network to put in 5G and operate 5G instead of 4G for all sorts of reasons, not least that most of your customers are probably still using 4G handsets anyway. But for those who have 5G, then they can connect via 4G initially, and then the network will decide to give them 5G connectivity as well, if needed, and if that's advantageous. But perhaps inside a factory, so some sort of enterprise type solution, which is built from scratch. Then inside that factory with user equipment, devices, which aren't smartphones, which are perhaps machine type communication, then we can perhaps start looking at just 5G absolutely from the ground. Meanwhile, the public networks can sort of evolve more slowly. But for now, in most networks, it's very much this idea of non-standalone 5G. So it's working with 4G. So what it means is that we end up with a overall architecture which looks very much like this. So we've got a core network, and we've got a radio access network, and we've got a choice, or we've got a combination of 4G radio access and 5G radio access. And the 5G handsets that we've got right now have got to use 4G first to establish connectivity. And then if everything lines up, the base station here, the 4G base station, can decide to bring in 5G connectivity, but only if this is giving good measurement reports saying that it can see 5G, and it requires a service for which 5G would be an advantage. So initially quite simple. That means we're still using a 4G radio access network and a 4G core, but of course eventually we want to evolve these as well. That should become in time a 5G or next generation radio access network, and this should become a 5G core as well. So 5G not only is about new ways of using OFDMA and also new features and things like that. It's also about trying to make sure that 5G works really nicely with 4G and gives us evolutionary sort of paths. So some of the evolutionary mechanisms are, for example, on the radio. So we can move from non-standalone to standalone in time, and we'll look at the evolutionary path for that later. How about dynamic spectrum sharing, which we're starting to see as a sort of added benefit of 5G, which means that you can have some spectrum which initially is 4G, but as you have more 5G users starting to want access to the system, you can sort of slowly turn that over to 5G. So dynamic spectrum sharing, more on that later. Perhaps in the infrastructure and the radio access network, again, we've got this notion of moving away from non-standalone to standalone. So that will make a difference. We've got additional features and initiatives like Open RAN. So Open RAN, lots of sort of initiatives going on in the background there, some of which are pretty active, others have been sort of suspended or different parts of the world. But Open RAN type architectures, we start splitting the base station into component parts to give us much more flexibility, which also then leads us to this notion of integrated access backhaul. So this is where 5G, we sort of acknowledge that certainly if we're using the higher frequencies for 5G, then we start looking at smaller cells. And if you've got a smaller cell, you know, suddenly the number of cells, small cells, increases massively. Do you really want to run fiber to each of those small cells? Is that something that we want to do as an operator? Or do you want to sort of keep a really good fiber connection to perhaps a good sort of well connected master, if you like, and just run radio links? So effectively microwave links off to the small cells which are working with the master. So we've got this sort of integrated access backhaul where we can have a radio connection using the same spectrum that we're using for the cellular access. In the core, we can't forget the core. I know this webinar is about the radio, but just in the core as well, there is some impact as to whether you are non-standalone or standalone, as to what form the core network should take. But hopefully we are catering for that, because we've got interworking solutions between 4G and 5G, and it is 4G and 5G. We don't really include 3G or 2G in that. Not when we're considering 5G. There are mechanisms, but generally in terms of the core, it's 5G, 4G interworking and Wi-Fi interworking as well. And then we've got something called the combined service-based architecture core, or words to that effect, generally proprietary solutions, where we've got a core network which uses the new sort of architecture from 5G, but also applies it retrospectively to 4G. So if you're looking at spending money on your core network now, but you want to future-proof it for 5G, then we can do that in a much easier way using the combined core. Okay, so let's get back to the radio. Let's get back to this part of the network. So the big picture is that we're still using OFDMA, so orthogonal frequency division multiplexing, but it's different. We're still going to have the configuration that we use for LTE. Largely, we're still going to have access to that, but we're also going to have access to other configurations. If you don't understand what I've just said there, I will describe that on the next slide. In addition, therefore, because we've got different configurations here, we can efficiently use new spectrum, including much higher, what we call millimeter wave. So the flexibility here is very much an enabler for using new spectrum. And because we use new spectrum, higher frequencies, then the characteristics of the antenna, the size of the antenna comes right down in size. If we move right up the frequency spectrum, the antenna size comes right down, and we can start using lots of antennas together, which means we can start using the mathematics, constructive and destructive interference to focus energy, beamforming, and this massive MIMO, massive multiple in, multiple out antenna systems. to gain access to a lot of the additional features that we need to support, perhaps new types of connectivity for new use cases, we use a much more flexible framework in terms of timing. So here we're showing time and frequency, but we've got a lot of flexibility, which we'll look at again a little bit later. And then finally, probably the fifth of the really big new pillars in terms of the technology is advanced channel coding. So we moved away from the turbo coding, which we used in LTE, and we're now going to be using something called low density with parity check. So it's quite an old mathematical sort of algorithm, if you like, which probably doesn't do it justice as a term for the mathematicians amongst us. But it allows us to take the data that we want to transmit and to put it through an algorithm which introduces a lot of dependencies within the data stream. Effectively, it gives us forward error correction. So if something arrives at the other end of the radio link, and radio links are notoriously, variable in terms of the quality, but if something arrives and there's quite a few errors, then it's fine. LDPC will be able to correct to a certain point. After a certain number of percentage of errors, it will break down, but it's good where there's errors. And that's what we needed for 5G, because we've got all that flexibility in terms of the way in which we're going to deploy it. So LDPC for the main sort of data in 5G new radio. Okay, so let's just have a quick look at the OFDM, orthogonal frequency division multiplexing. So we've got a diagram here where we're showing frequency left to right. And what we're saying is, if we had quite a wide band of data, quite a wide band that we want to use, and generally when we talk about wide bands, we're talking about higher data rates. So if we want to send a lot of data from A to B, we're looking at quite a high bandwidth. And I think a lot of people understand that. High data rate means high bandwidth. Very often we use that interchangeably. There's a real difficulty when we use radio and we use wide bandwidths in certainly urban environments. We've got lots of buildings, lots of radio reflections and things like that. To use a full wide bandwidth just as a single sort of transmission is really difficult for the radio systems. So what we do is we split it into much smaller bands. And here you go. So here we're showing different transmissions being transmitted, perhaps on the frequency spectrum there. They're spaced at 15 kilohertz, perhaps. Well, they would be if it was 4G, they would be spaced at 15 kilohertz. They're really specifically spaced. There's a lot of maths that go into this. We've actually chosen, for example, we've got a blue one there being transmitted. So that represents a transmission. We've chosen the spacing for the red and the green such that when you look at it, there's the point of nominal transmission. But 15 kilohertz either side, it's contributing exactly 0 power at the point that the blue transmission is being transmitted. So that means it's orthogonal. These are as different as possible where it comes to the actual power points. That's probably about as simple as I can make it. So mathematically, this is really difficult to do. In fact, we couldn't even do it until about the year 2000 at the silicon level, because we need very linear power amplifiers at the silicon level. So this only really became something we could use around 2000. For those who remember WiMAX, we initially saw it in WiMAX, and then it was applied in a much better way to LTE. Right, so the point is that, there you go, in 4G, the spacing here is fixed. In 5G, it's flexible. In 5G, we can vary this. And that's possibly, can I say the key difference? One of the key differences between 5G new radio and 4G. Why? Because it changes quite a lot in terms of the radio. So here you go. So below 3 gigahertz, if you've got spectrum below 3 gigahertz, and most of the operators around the world will have this, 15 kilohertz subcarrier spacing, as we've got currently with 4G, is ideal. That's what LTE was designed for. Outdoor big cells, lower than 3 gigahertz. If you look at perhaps the second option with 5G, now remember, any of these from that first one, anything below that first diagram there is not available to us in 4G, but in 5G they are. So if we wanted to move above 3 gigahertz, then we could use a subcarrier spacing of 30 kilohertz. And now this is great because things change. You know, the way in which we've configured the radio changes. It doesn't just change the frequencies, it also changes the symbol duration as well. So the handset, the rate at which it's looking at the incoming signal. So here it could be looking now. Here it would need to look at the incoming signal twice as fast. Now. But that means that actually this is okay, perhaps for smaller cells above 3 gigahertz. And then with 5G, we can go even further, 60 kilohertz subcarrier spacing. So this is now clocking 4 times as fast as this, but actually the frequencies are spaced 4 times as wide, so 60 kilohertz. So this will be good perhaps for indoor unlicensed, and maybe this one for millimeter wave. So we've got a lot of flexibility in 5G. So for those really diverse deployments in terms of spectrum and size of cell, then we get some real benefits in using 5G instead of 4G. Now, I did say that this is clocking 4 times as fast as that one. So 4 times the frequency spacing, but 4 times as fast in terms of the handset clocking. When I say clocking, if you're a radio engineer, I don't mean clocking as you know it. I just mean the rate at which it's looking at the incoming signals. Right, so if you think about that, it means that if we were to use this millimeter wave, perhaps in some sort of factory setting, some manufacturing, suddenly we can really think about the latency, the speed at which the data is being transferred from A to B. Now, really quick, that latency can come right down. So systems which are perhaps using millimeter waves, in a very crude way, I could say, well, these are 4 times as fast. Or if you like, the delay is a quarter that we might expect from LTE or from the 15 kilohertz 5G configuration. So we get benefits already in terms of latency. So this might be great for inside a factory, which tends to be quite small in terms of coverage area, where perhaps the latency, because it's machine type communication, has to be very much lower. For those who are interested, each of these would also be configured pretty much dynamically, very dynamically, just as they are in 4G LTE for the different modulation schemes. So these are representing, if we look at these in terms of time, these would be represented by symbols, and on those symbols we could then carry a number of bits depending on how complex the modulation scheme is. So we need to manage all of this, and it's not easy because I've said earlier that 5G could be made up of carriers of 100 megahertz in frequency range 1, or perhaps even 400 megahertz in frequency range 2. But we've got all these different configurations. First thing to say is that in those 2 frequency ranges, not all configurations are available to us. But if they are, so for example, in frequency range 1, we could organize 15 kilohertz subcarrier spacing together with 30, together with 60 within the actual frequency carrier itself. And that's something that we've not really done before with LTE. We started sort of looking at using different subcarrier spacings, but with 5G, in time, it will be very much a thing. I think for initial deployments, a lot of operators just kept it really simple, and they just went for 30 kilohertz subcarrier spacing. But already we should be thinking, well, sometimes it's better to go for 15 kilohertz subcarrier spacing. And for some use cases, for some things that we're trying to do, or some things that customers are trying to do within the cell, sometimes it might be better to go for the lower latency, or if you like, the perhaps a wider subcarrier spacing at 60. Sorry, 60. So this is just showing that we can manage it. And we've got something called bandwidth parts, which allow us to manage what type of subcarrier spacing we've got in which part of the carrier. There are some golden rules. We never mix those, but in terms of changing them, if conditions change, if customer mix changes within the cell, potentially we're going to be able to change that. So certainly that will all get more dynamic as we move into the future. And of course, in terms of timing as well, we did say that it does affect the timing. Look at that. 15 kilohertz subcarrier spacing. Remember, that's the only one that we had available with 4G. We've also got these available with 5G, depending on the frequency band. So what we're saying is that now looking at this in terms of time, so that whole thing there represents 1 millisecond. So if it's 15 kilohertz subcarrier spacing, we've got 14 symbols in a subframe. If it's 30 kilohertz subcarrier spacing, we've got 28 symbols in a subframe, or 56 or 112. So you get the idea. Now we're not getting something for nothing here, because don't forget the subcarrier spacing is twice as wide here as it is here. But this gives us a lot of flexibility. So the way in which we can use the timing and the rate at which we get data from A to B, we can be very flexible as well. And in fact, we can be even more flexible, because in the system, as we were redesigning it for the flexibility, we've introduced things like mini slots. So rather than with 4G, where we were sort of looking at a whole slot in terms of a minimum amount of resource, in 5G, we can look at a mini slot. So we can actually ask a device to transmit, and we can look at just mini slots, just 2 symbols, or 4 or 7 symbols. But anyway, we can be a lot more flexible with 5G. So in terms of the way in which we organize in time, it is a lot more flexible in the same way that 5G is a lot more flexible in terms of frequency compared to 4G. So when we put it all together, the frequencies, the subcarriers, these can be very flexible. The timing can be very flexible as well. So we end up with a resource grid where we just need to map different customers and different type of services onto the resource grid, maybe making some of it available for our enhanced mobile broadband, maybe device to device, the side link that's just been specified in release 16 and beyond, perhaps multicast, perhaps ultra reliable and low latency communication. Now that's interesting, because again, we've introduced some more flexibility. So we've already assigned some resource to one customer, and suddenly we have a ultra reliable and low latency customer immediately wanting resources. We can actually just take the resources off the original customer and then tell that customer about it later. Just additional features in 5G that weren't available to us in 4G. So really flexible in terms of frequencies and time. So just to take us back to that original statement that I made, that was very wordy. Let me just sort of put a little bit more detail around that. So this is supporting the existing mobile broadband business model. If that shape there, if the volume represents network capacity, what does 5G do for us? So first of all, we gain access to the increased spectrum because we've got the flexible frequency subcarrier spacing. So flexible air interface. Interestingly, if you move right up the spectrum band, the higher you go, the more isolated your cell will be. So what I'm saying is, the higher the frequency, the lower the effective range of a cell. Now, if you can imagine one operator using a very high frequency to give us a cell footprint here, if another operator uses the same frequency quite close by, at really high frequencies, it won't make that much difference necessarily in terms of interference. Now, that means that we can start thinking about sharing spectrum or using unlicensed spectrum, which at the lower frequencies would have been very difficult to do, because lower frequency, energy is usable at quite long distances. Hence, other cells using the same frequency can provide a lot of interference. So here we are, higher frequency, access to increased spectrum. Higher frequencies means all of a sudden we are enabling unlicensed and shared spectrum. The flexible antenna systems also give us the access to the increased spectrum as well. So we need that in place to be able to properly use that increased spectrum. 5G also gives us increased efficiency. So access through, again, the flexible air interface and again, multiple antenna systems. So increased efficiency, because the frequencies can be much higher. We can start using multiple antenna schemes. We can start using the maths, the constructive and destructive interference to focus the energy. And then finally, just on this diagram, if we've got to put in increased number of base stations anyway, which I think most people are, pretty much agreed that will still have to be the case. We're going to be much more efficient putting the base stations in compared to 4G. We've still got to do it. But a much more flexible base station architecture that we get with 5G compared to 4G makes that easier, potentially more cost effective. We have the flexible backhaul, the integrated access backhaul, and we also have the 5G, 4G, and Wi-Fi integration, which hopefully we're going to be pretty happy about. So 5G brings improvements in all three axes. So that's to support the existing business model. So what about new use cases? What about new business models? So 5G really does give us the new opportunities for existing operators, for sure, because remember, we are also going to look at the latency and the reliability and the power. So 5G is going to be bringing us advantages to the existing telecoms operators, but also new organizations. So those who want to use 5G to augment or supplement Wi-Fi, or those who want to use 5G to provide coverage just focusing on factories or just focusing on indoor solutions. Remember, 5G gives us or puts us in a much better position to provide isolated connectivity if we're using the higher frequencies. We can't do that with 4G. Well, we can do that to a certain extent with 4G by careful power control, etc. But 5G, in terms of the higher frequencies, we do get a lot of isolation. And of course, anyway, 5G was also developed to support all this. In any case, one of the very starting points of 5G in terms of the development was to look at the massive range of new use cases. Just too many to develop a system around, so we did categorize them. And initially, we based a lot of the developments on enhanced mobile broadband, but coming through now, really with release 16 and 17, we're doing a lot more on ultra reliable and low latency communications, some of which we've already touched on with 4G, but 5G should be much better placed to provide that sort of enabling features. Massive IoT, or even some high data rate IoT as well, and vehicle to everything as well. So supporting the new business models, how does 5G new radio do it? So efficient, more efficient high-speed data, the focusing of the energy using those antenna systems. The benchmarks was 3 times more efficient than LTE advanced. So we can focus the energy better in 5G, gives us opportunities to do that. Again, access to higher frequencies, therefore isolated cells, therefore shared spectrum or maybe unlicensed, and therefore better place for private 5G networks. Now, there's a lot of thinking to be done around this. all I've done is massively simplify it just with 3 bullet points there. But in general, 5G is a better place than 4G for this, or certainly will be in time. It also gives us low energy, so good for Internet of Things, good for machine-to-machine communication. Low latency as well on both the radio and, if you look into the actual core of the network, if you look at the way in which we handle the data, potentially end-to-end as well. Say end-to-end through the system, but some of that might mean moving some of the core network elements down to the base station. So the evolutionary rollout really is getting back to basics again. So initially we are looking at connecting via 4G, and if everything's in place, so if it's a 5G device and it tells the network that it's a 5G device, which it should do, if we require 5G connectivity, if the 4G base station asks the device to report what it can see, and it can see a 5G base station here and reports that in, all of that is in place, that master ENOB there, the master 4G base station, can ask the device to add 5G connectivity. And that's where we are right now. It's called ENDC, dual connectivity, so 4G and 5G. We connect via the EUTRA, or if you like, 4G first, and then the new radio, so E and then N, so ENDC. So based on 4G procedures with minimal 5G procedures, at the moment, a lot of operators have simply just co-located 5G with 4G. So where we're moving to is the right-hand side. So let me just pop that up first. So this is where the device could connect to 5G first. So connect to 5G first, and then actually the 5G master could bring in extra, maybe higher frequency capacity from a secondary, and that could be 4G or 5G. So this really represents where we're going to, which also shows us that actually 5G and 4G could be working together for many years to come. There's no reason why not. One of the really key things here is that we've actually changed over to 5G RAN, 5G radio access network, and a 5G core. So this is again dual connectivity, but this time we can connect via new radio first, and then if we wanted to, we could add EUTRA, so 4G. And there's a halfway house where we're still doing the 4G radio first, but we've already sort of transitioned to a 5G infrastructure. So if we do 4G radio first, we call that non-standalone new radio. And if we can just connect via 5G immediately, we can call this standalone. So the question is, has this got to be a really big sort of changeover as we move through this evolutionary series of configurations? And the answer is not as much as you think, because remember, we've got the combined core. We potentially have got, in terms of the radio, we've got a spectrum, we've got dynamic spectrum sharing, potentially. And then the next thing is that actually we can configure the base stations, the 5G base stations, to say whether they are initially selectable or not. So we could actually compel that device to keep connecting via 4G, or we could, in certain areas of the network, tell the device to connect to 4G, let the network decide whether to connect 5G, and in other parts of the network, this is in theory, in other parts of the network, we could just say, look, yeah, you can connect directly to 5G to start. Okay, so time's getting on. I just need to look at some really key features. So first of all, dynamic spectrum sharing. Traditionally, if we've got 4G spectrum, we want to add additional capacity, but this time with a newer technology like 5G. Generally, it would be new spectrum, new antennas, and new RF equipment. There are variations on that, but essentially that's what we're looking at. For dynamic spectrum sharing, what we're saying is, look, if you've got a big chunk of spectrum anyway, and you're using it to 4G, using it for 4G, we could do a sort of slow changeover to 5G dynamically as more customers take up 5G as a service in the network. So that's the simple version of it. Just to show that it's a real thing, Nokia are already doing this. This is already out there in the field. So the Nokia solution is they will offer between 600 and 2.6 600 megahertz and 2.6 gigahertz. They'll offer wide area 5G coverage, gradually allowing you to reform from 4G to 5G. And of course, anything above that spectrum is 5G only anyway, so we don't have to worry about dynamic spectrum sharing. So that's one key feature. Second key feature, how about this? So supplementary downlink. If we had a cell and we wanted to add additional capacity, we can do that via another supplemental downlink. So what we're saying here is that that cell there could be lower frequency, and if we've got slightly higher frequency available with more capacity, we can also make that available within the same cell. So it's in the downlink, you've got a secondary cell, it's used in parallel with the normal cell, and it improves the downlink capacity. So you've got coverage, and they can make available the additional capacity to those who need it. If a device is on the edge of the cell, then maybe we provide them with the capacity using the normal primary cell. So that's supplementary downlink in 5G. We've also got supplementary uplink, which is really interesting, because if you look at this, if we are using 5G but at a slightly higher frequency, or even a much higher frequency than 4G, then the usable cell radius will be lower. But there's an imbalance in the downlink and the uplink. So what we're saying is, the G node B, which can throw out lots of power, can get good coverage in the downlink, but in the uplink, the poor old devices can only throw out a certain amount of power. So what we're saying is, we can tell the device, look, if you want to send a lot of data, just switch to a supplemental uplink, which will be on a lower frequency. So really key feature there. Unlicensed operation, we've introduced this with LTE and release 13. So we've got an unlicensed cell there, unlicensed secondary cell, which could be made available once we're connected to a licensed primary cell. So when we say unlicensed, we mean this is using spectrum which is in the unlicensed band and unlicensed band, possibly an ISM band, industrial, scientific and medical band, the same as Wi-Fi, the same as Bluetooth, or those bands which are the same sort of use. But in 5G, in new radio, the unlicensed spectrum, we can connect via unlicensed from the off, at least from a standards point of view. We need this to be checked against different geographies around the world and the different regulations, etc. But essentially what 5G itself as a standard allows us to do is connect via unlicensed, initially in these bands. So there you go, initially in these bands. So we can connect directly via unlicensed, and then we can have unlicensed secondary cells as well. So we've actually moved it on from LTE to give us additional features in 5G. Just coming towards the end now, but another really good feature is integrated access backhaul. So all we're saying is we can use the same spectrum that we're going to use to connect the customers, the actual end user equipment there. We can use the same spectrum from the same band to extend coverage from a donor, so from a master site through perhaps to a small cell here, without having to connect fiber to those small cells. So different modes of operations for the integrated access backhaul as well. So that's another good feature. Multiple antennas, I'm not going to spend a lot of time on this. This is so complex, it's untrue. We do have other webinars on this. But MIMO, so the multiple in, multiple out antenna systems, you can see there are multiple antennas and possibly multiple antennas on the handsets as well. Great for low frequencies. So we've been using this for quite some time. It's been available to us. We've started to get to grips with it, but it should really start coming into its own in 5G, as should beamforming, because beamforming is good for higher frequencies. And of course, with LTE, we don't really see too much in the way of higher frequencies, certainly not compared to 5G. So we've got different ways of forming and using the beams. It's very flexible. As we move forward in time, as processing improves, we will get more focused, we will get more efficient with the antenna systems. But again, 5G puts us in a really good position compared to 4G. Just thanks to OpenSignal, really just for some really good data, because they collect this from the handsets. So this is just via their app, and they put this out via their websites occasionally. This goes back just a while, just because to me, it represents one of the sort of initial looks at 5G data. And from a customer point of view, although customers don't really need 150 megabits per second, but to see that as an improvement over LTE at 46 megabits per second is quite something. So this is just a snapshot of what actually 5G new radio can mean to the customers. So just onto the last slide then. What we've done here is we've just brought together those, do you remember those 5 big key things from 5G new radio? So scalable OFDM, advanced channel coding, massive MIMO and the advanced antenna techniques, mobile millimeter wave as well, and then finally the self-contained slot structure and the shorter timing. And just to get some sense of what this is doing for us, because they're the key differences compared to 4G. So first of all, in terms of efficiency, everything to the left of the black line, the scalable OFDM based radio interface gives us more efficiency. We might say cost efficiency, actually. Advanced channel coding and the massive MIMO for focusing the energy. If we're looking at capacity enablers, it's the massive MIMO. So the advanced antennas for focusing the energy, because if you're focusing in one direction, it means you're not causing interference and therefore giving you much better usability in other directions. And the mobile millimeter waves, because there's a lot of extra spectrum available. Low latency enablers, so the scalable OFDM and the way in which we use that, so the slot structure. And then finally, low power as well. We've not said too much about that, but that's again built into the system, minimized always on transmissions, so you don't have much in the way of sort of pilot channels. So we do when other things are being transmitted, but we don't just have them being transmitted across the resource grid when nothing's happening. So in 5G, we are more efficient. And also lower frequency, lower bandwidth options as well. That should increase the range, because LTE is great at high bandwidth stuff. We've had to modify it for low data rate and high range or low power connectivity. We call that LTE-M, or even better, we go beyond LTE and call it narrowband IoT, but 5G should be able to do that as well. Okay, right. So that's all I've got for you really in terms of the slides. But I saw a couple of questions go through. So yeah, first of all, just a housekeeping point. Will there be a recording? Yeah, we'll send out a recording. We'll send out a link to a recording. But if I just take some of the questions on the question and answer pod. So can we use 5G from balloons, planes, or satellites? So I believe that in the upcoming standardization process, the non-terrestrial 5G is going to be looked at. I did some work a while back with the guys from, well, they were still Google then, but Project Loon, which were looking at base stations on weather balloons. And basically that was a 4G base station on the weather balloon. So given that we've got the same sort of configurations available to us in 5G that we had in 4G, and all the additional configurations as well, there's no reason why it shouldn't be applied to weather balloons if that's what you want to do. Bearing in mind that Loon is now just sort of wrapping up. But yeah, in terms of satellites, I believe lots of work being done on that. Combined, just had a question on combined core service-based architecture. Is this same as dual mode cloud? Yeah, it will be, Andrew. So pretty much different terms used by different manufacturers. Just another question: what are the prices of the courses? All right, I'll leave that to Paul, perhaps to take that one after we finish. Cameron, can you come on to an ORAN? Is it the next step? Will companies adopt it? Jury's out a little bit. So as a concept, as an open RAN concept, there's plenty on sort of splitting the base station, so we can split it into a sort of centralized unit, a distributed unit. So that's absolutely coming to 5G no matter what. So you're going to get that flexibility. So all O-RAN then does really, I mean, it does a lot of things, obviously a lot of things. So O-RAN, Open RAN, C-RAN, they're all slightly different flavors on the same sort of topic area. But we split the base station, and then we just got to make sure that we manage the functionality and in terms of where that particular part of the base station sits. Now, obviously the distributed unit, or at least the remote radio head, has to be wherever you want the cell to be centered or the sector to be centered. But the other bits can actually be placed pretty much anywhere else. You can even have your control part of your centralized unit on the Amazon Web Service. So I think from that respect, yes, we're going to see a lot of the splitting of the base station. We will see a lot more flexibility, but which flavor actually wins out is another question. I think we were making a lot of progress on one of those systems, and then all of a sudden we sort of halted some of the development just for a short time until we sort out some of the politics, I think. Yeah, so I'm just looking at some of the questions going through. So what millimeter wave bands have been validated by the ITU? I sort of knew we were going to get that question. So let me just bring this in. So this is just a slide from one of our courses. So this is what's been standardized within the specifications. And in terms of the ITU, they're always sort of one step ahead because of the cycle on the World Radio Conference. So they're always standardizing ahead. So for example, the ITU have gone beyond what we find in the third generation partnership project specifications in terms of frequency range 2, which initially sort of stops at this N261 band, but they've already specified right the way up into the 70 gigahertz band. So if you want to send me a quick email, I can send you a slide on that if you want that, the ITU figures for the spectrum. We can do that. So Mohammed, if I understand well, 5G will adopt only TDD. Actually, just back to this diagram again. So these are pretty much the first tranche or second tranche actually of the standardized 5G bands. So you'll see that anything above 3 gigahertz would tend to be TDD, plus a few selected additions as well. Anything below 3 gigahertz would tend to be FDD, mainly because of, one main reason is because of legacy deployments. The second reason, probably the biggest reason why we've gone for TDD above 3 gigahertz is that the frequencies tend to be higher. There tends to be more antennas in the antenna arrays that we're going to be using. And when you start looking at it from that point of view, things like the reference signals that you need to efficiently use those antennas goes up massively. So TDD, the same transmit and receive frequency, gives you channel reciprocity, which means we can use the uplink to estimate the downlink and vice versa, which is a massive advantage at the higher frequencies. Does that answer that question, Mohammed? Okay, so how we do just after 3. I'm quite happy to keep going for a short time if other people are. So just one from Isaac. So in ENDC, which is a version of 5G that we've got now, since the device is connected to 4G and 5G, are measurement gaps handled independently of each radio leg, or doesn't have to be synchronization? Yeah, so yeah, they can sort of be handled that's a really good question, actually. They can be handled independently because of 5G base stations. So the G node B can actually ask the device to take its own measurement reports. So that's, even though I've said we're using 4G radio procedures, 5G has just got one or two additional procedures that it can use, and actually asking for the measurement reports is one of them, actually. So yeah, it can be independent. Right, Martin. So when a device is using a master eNodeB and a secondary gNodeB, how do we refer to the 5G connection? So it's a secondary cell group connection. So it's yeah. So there are good question. There is specific terminology that we use, but it's a secondary cell group connection as opposed to the master cell group connection. So just from my 5G antennas, does the antenna following the user in terms of hardware mini antennas, or it's just software feature using phase shifting? Yeah, so so it would be software in general software. Yeah. So a bit like just a phased array antenna system that you might have seen at university. And then is carrier aggregation necessary in 5G, and would ANR resolve the issue of redundant neighbors? Yeah, that's going to require quite a big answer. Actually. If you just send me, I'm not sure who that was actually, it's anonymous on my question. If you could send me an email, I've got an answer to that. I probably need a little bit of time to explain the answer, if that's okay. Okay, and okay, finally, just from Martin, with a master eNodeB and the secondary gNodeB operating in an eUtram, what type of core network will be used? So again, a really good question. If I can just go back to almost there to this diagram. So the rules are, if you're connecting, or according to the standards, rules are that if you're going to be connecting via the master first, i.e. you are using standalone 5G, then according to the standards, we should have moved the infrastructure over to a next generation RAN and a 5G core. So when the NG RAN moves to 5G, the 5G core moves as well. So that's according to the standards. I'm not really now workarounds or anything like that, but that's according to the standards. Fantastic, great. I think we're out of questions. Paul, I don't know if you want to jump back
thanks,
in.
Tony. That was great, and it's good to see so many questions as well. So just as a reminder, the recording of the webinar will be sent out to you all within the next couple of days, so look out for that, please. And there's a question regarding further training. I mean, here's just a few of our training courses that specifically address 5G new radios. We've got a 5G RAN, air interface, and cell planning course. Now, these courses are on-demand online training courses. They all feature course books, videos, full tutor support, and continuous assessment and digital badges for successful completion. Now, these come in, there's a question about pricing. These come in at £1,500 per seat, but there are, of course, team and enterprise-wide options as well. So if you would like any more information on these courses, please email us at info@roadcastle.com. But yeah, I'd just like to say thanks for all attending. It's great to see so many people here. Yeah, thanks, guys. Great to see old friends and you as well. So I recognise quite a few names on the training. So great to see you all. Hope you found it useful, and hopefully we'll see you on the next one. So take care, everybody. Speak soon.